This video covers Newton's first, second, and third law. A couple of things that are really important to remember about forces is that the unit for force is a Newton. This is made up of kilograms meters per second squared. So kilograms meters per second squared are the base units for a Newton. A force is by definition a push or pull, and they can exist through physical contact or no physical contact. So the ones that we're going to talk about most in this section are tension, friction, applied force or normal forces, and gravitational force. Ones that we'll talk about a little bit later are electrical forces. Newton's first law is the law of inertia. Remember that inertia is a resistance to change in motion. This has to do with the mass of an object. Remember that weight, or the force due to gravity, is how your mass is affected by gravity. So, force of gravity, weight, all of this is equal to mass times gravity. How your mass is affected by gravity. Remember that mass and weight are not the same thing. This is one of the most important things to this section. Mass and weight are not the same thing. Mass never changes, whereas weight is affected by the gravity. So if you were to move to a different planet, your mass would not change, but your weight would be different according to the gravity on that planet. Another very important thing to remember is that the gravity that you input here into G has to be a positive 9.8. The negative is going to come out later in your equation. Again, Newton's first law says that an object in motion remains in motion in a straight line and at a constant speed, or an object at rest remains at rest unless acted upon by an external, in other words, unbalanced force. What this is basically saying is that if all the forces are balanced, then the sum of the forces is zero. If all the forces are balanced, that means that the acceleration is zero. So there's two situations that you can have an acceleration of zero, when you're either moving at a constant speed or at rest. Remember that this symbol down here at the bottom means sum of, sum or total. Remember that dealing with force problems, we need to always draw a free body diagram. What that means is we need to draw all our forces acting on our object. So the forces that we normally deal with are weight, which you can label as mg or F subscript g. And this is always drawn from the center straight down. The other forces are a normal force. Again, this normal force is created by a surface, so it's always drawn perpendicular to your surface. Tension is going to be represented by a T, or force, with a subscript T. I normally like to use T, but if you want to use either one, it's okay. So when you have a tension, this will always be drawn away from your object. Normally, tension will occur when you have ropes or cables or strings or anything like that. And our last type of force is friction. Friction I will normally write as a cursive F, but again you can write it as a capital F with a subscript F. And this is always drawn opposite the direction of motion. If a problem tells you that it's moving at a constant speed, or if it's at rest but you see that there are forces acting on it, then it must be in equilibrium. What that means is that the forces have to be balanced, even though it doesn't tell you that the forces are balanced. So something like an object moving at a constant speed, and it's being pulled by a string, then it's implying that there is friction involved. So again, if it's moving at a constant speed or if it's at rest, then it has to be in equilibrium. So a couple of tips for helping you solve these problems. You always need to draw a free body diagram for every single problem, even if it doesn't ask you to. This will help you visualize the problem, and it'll help you understand if anything needs to be broken down to components. So for the next part, resolve anything into its components. What that means is if you have a force acting at an angle, then what I want you to do automatically is start solving for the force in the x direction and for the force in the y direction. For these, it will not always be cosine on the x direction and sine on the y direction. So you need to be careful according to what angle you're given, which one's cosine and which one's sine. Also, make sure that you write the equations of equilibrium. What that means is you need to write the sum of the forces in the x direction and the sum of the forces in the y direction. Again, this will help you understand what's happening in both directions. And remember that you can, because these are vectors, you can treat them independently. And once you've done all of that, then you can solve for your unknowns. So first off, with a very straightforward problem, it says a 10-kilogram box is being pulled across the table to the right at a constant speed with a force of 50 newtons. Calculate the force of friction and calculate the force normal, or the normal force. So here I've included a picture for you, but even if it didn't include a picture, and even if it didn't ask you to calculate the force of friction, you'd have to assume that there's friction involved, or that there has to be an opposing force, because it does say constant speed. So here I have a force being applied of 50 newtons, and we want to calculate the force. Because we are moving at a constant speed, then the sum of the forces in the x direction must be equal to 0. So another way to write that is that the force applied minus my force of friction is equal to 0. Therefore, if I apply a 50 Newton force and I want to solve for my force of friction, then my friction would have to be 50 newtons. Again, you could have seen this, but when the problems get a little bit more complicated, it's a good idea to go through these steps. Now here, I'm asked to calculate the normal force. So that's this piece right here. Now, one of the biggest problems that I see is that people automatically assume that the normal force is always equal to your force of gravity. And we're going to see situations where that is not true. In this case, the normal forces are only force in the y direction. So the sum of the forces in the y direction is our normal forces pointing upwards, so it's positive. Gravity, or the force of gravity, is pointing down, so it's negative. And we want to set this equal to 0. Now, right now, we're not given any information, but we do know that our box was 10 kilograms to begin with. So, if 10 kilograms is our mass, well then mg becomes 10 times. And here I'm going to go ahead and use 10 for gravity to make our numbers a little easier. So we get 100 newtons as our force. So if I want to get normal force by itself, then our normal force is equal to my force of gravity, or 100 newtons. So now we have another example. Suppose the same box is now pulled at an angle of 30 degrees above the horizontal. Our box still has a mass of 10 kilograms, and it's still being pulled with a force of 50 newtons. But now these 50 newtons are being applied at an angle. So here, if we want to calculate our force of friction, now it's not equal to our force applied. So to write the sum of the forces in both directions, I want to look at my forces in the x direction. Well, here, if I have a force that's at an angle, then I want to write this as my force applied times the cosine of theta. And this is my force applied in the x direction. Now I want to do the same thing for my force in the y direction. So that's my force applied in the y direction is equal to my force applied times the sine of theta. So, again, to write the sum of the forces in the x direction, I want to do force applied, cosine theta. Again, this is my force in the x direction, minus friction. Again, is equal to 0 because, again, my sum of the forces in the x direction have to be equal to 0 in order for this object to be still moving at a constant speed. Now, my sum of the forces in the y direction, well, if you notice, I have 3 forces in the y direction, so my normal force is no longer equal to my force of gravity. So I have 2 upward forces and 1 downward force. So when I start writing this, I want to write, and here I'm going to go ahead and write normal forces in N. So this is normal force, which is upward, so it's positive, plus my force applied sine theta. Again, this is my force applied in the y direction, minus my force of gravity. Again, it's negative because it is pointing downwards. That's why we're not putting a negative in 9 point in G, because we're taking the negative into consideration here. Again, because it is moving at a constant speed, then my sum of the forces is equal to 0. So if I'm trying to solve for my force of friction, well, this simply becomes my force applied times the cosine of theta is equal to friction. So we said my force applied was 50 newtons, cosine of 30 degrees is equal to 43.3 newtons. So that's my force of friction. And then the second part asks us to calculate our normal force. So here I want to get normal force by itself, so I want to move everything to the other side. So my normal force is going to be equal to my force of gravity minus my force applied times my sine of theta. We know that mass times gravity was 100 newtons, and my force applied times the sine of theta is 25 newtons. So my normal force is therefore equal to 75 newtons. The last part is when you have more than one force acting at an angle. So here it says the sum of the horizontal and vertical components of the tension are equal to 0 if the system is not accelerating. Another way to say that, if you are not accelerating, then you're either moving at a constant speed or you're at rest. Here we can see if nothing is moving, it must be at rest. So first things first, when I have a situation like this, I want to draw a free body diagram. So I know you might think that a free body diagram is already shown, but that's not true. So we're going to draw it anyway. And the forces that I'm going to draw are the forces affecting my knot in the center, because on my knot, there are 3 different things acting on it. So on that knot, I have the force of gravity acting downwards. I have tension 1 acting at an angle. And I have tension 2 acting at another angle. So here it says that this piece was 45 degrees. And that this piece is 30 degrees. So for me, I think it's a little easier to see the forces if I write the angles down here instead. So because of our properties from geometry, I know that this angle is 30 and this angle is 45. So first things first, I want to solve for the components of my tensions. So here on this side will be tension 1 sine of theta. Down here will be tension 1 cosine of theta. And I'm going to label these as theta 1s. On this side, we have tension 2 cosine of theta. Now, because this is pointing to the left, I want to make sure that I draw or I write in my sum of forces as a negative. And we'll see that in a little bit. And this piece becomes T2 sine of theta. Now, I want to write the sum of the forces in the y direction, and then the sum of the forces in the x direction. So, in the y direction, I have 3 different forces. 2 of them are pointing up, and 1 of them is pointing down. So, I have T2 sine theta pointing up, and this should be sine theta 2. Plus T1 sine theta 1 minus mg, and all of this is equal to 0. Now I want to write the sum of the forces in the x direction. In the x direction, I have 2 forces. So I'm going to write the positive one first. T1 cosine of theta is positive because it's going to the right. And T2 cosine of theta is negative because it's going to the left. Now, both of them are equal to 0 because, again, this object is at rest. So, what I see here are 2 equations with 2 unknowns. So, substitute. What I want to do is substitute T1, and I'm just rearranging this right now. T1 cosine of theta is equal to T2 cosine of theta. And T1 is therefore equal to T2 cosine of theta 2 divided by cosine of theta 1. So now that I've labeled T1, I can go back and substitute it in for T1 in the other equation. So for that, I'm going to go ahead and use a different color. Here, this becomes T2 sine of theta 2 plus, and I'm doing my substitution here, T2 cosine theta 2 divided by the cosine of theta 1. So all of that got substituted in for T1. Now I'm going to go back and put sine theta 1. And because I know that I'm going to try to solve for T2, I'm going to go ahead and move mg to the other side now. So it becomes a positive mass times gravity. Now here it might look a little messy, but my goal is to solve for T2. And there's a T2 in both of these sections. So all I need to do is factor out a T2. And I'm left with sine theta 1, actually sine theta 2 plus cosine of theta 2 times tangent theta 1. You could have left this as sine theta 1 divided by cosine theta 1, but it's a little cleaner if we just change it to tangent now. And again, our last part is to solve for T2. So make sure that you plug in all of your numbers in your own calculator and double check that you get a value very similar to mine. Make sure that when you put this in the calculator that you are putting the correct thetas into each of the different angles that we have here, and that you do cosine times tangent first before you do a plus sine theta 2. You should have gotten a value of 107.6 newtons. Now, this is only the tension in one of our strings. But if you go back over here, you notice that we have a function already, or we have an equation already for T1. So now that we know T2, all we have to do is plug it back in and solve for T1. So T1 becomes 131.8 newtons.